Okay, I start?
Yeah, okay. So let's start with the fourth lecture by Horacio. Continuing with the same topic.
Well, my lecture today is about entanglement and symmetries, and it's based on recent works with Marina Huerta, Javier Magán, and Diego Pontello, and one of them is put in the archive just a few days ago. This subject is, as we will see, is very much related to the subject of other lectures on generalized symmetries, and we will see these symmetries in a slightly different way. So how the story begins. So let us come back to the idea that we have algebras and regions, and we want to know how they are related, how this net of algebras, there are algebras attached to different causal regions in space-time, how they can be, what can be the features of these nets. So let us start reminding us that for each algebra we have another one that is like the complementary algebra, which is the commutant of the algebra. And the von Neumann algebra has this interesting property that are equal to the double commutant, the commutant of the commutant. And this defines what is an algebra. An algebra is one that satisfies this relation, some set of operators satisfying this relation. And we have something very similar for the causal regions. For the causal region, we have a complement, the causal complement that is just the points. If this is a causal region, this diamond, the causal complement is all that is outside, in the sense that this is space-like separated. And again, the causal regions are the one that coincide with the double causal complement. So very similar to the thing that is happening with the algebras. And in fact, this structure is something that can be enlarged to lattices. Lattices here is the meaning of this name. Lattices is just order sets that have always a supremum and an infimum. For example, if you have causal regions, the biggest causal region that is smaller than the two is the intersection, and this is also a causal region. And the same happens for algebras. The intersection of two algebras is also an algebra. And you can also have the causal region generated by two causal regions, which is just the union and then double causal complement. And the same for the algebras. You have the algebra generated by two algebras is the union, the set union double commutant. So, and this, for example, this algebra is the smallest algebra containing the A1 and A2. So we have some similar structure, and we want to understand how they mix together these structures in a quantum field theory, where you have algebras attached to causal regions. So the minimal requirements for any quantum field theory is that you have the assignation of algebras to region satisfies the ordering, in the sense that an algebra for a smaller region, R1 is included in R2, has to be included in the other algebra, because it's just the idea of locality, the idea that the operators that are attached to some algebra are local there. So it has to be, they also have to be present in a bigger region. And we have also this idea of causality, that the operators in some region have to commute with operators outside. So if I take the algebra of operator outside, the algebra inside have to be included in the commutant of the outside part of the algebra outside. That is this causality axiom, let's say. So these are cannot be avoided, this axiom. But we can enlarge the set of axioms to make the relation between algebras and regions the maximal possible one, the maximal harmony between algebras and regions. And we can think this is perhaps not the case for all quantum field theories, but for some particularly complete quantum field theories. And then we would impose, for example, we would impose that the algebra, the commutant of the algebra outside is just equal to the algebra inside, and this is not, it's not bigger, but it's equal. This is called Hug duality. And you can also think that the algebra for two regions, for the generated set of two regions, is equal to the generated algebra. So, and this is called additivity, and essentially means this action essentially means that the operators in a bigger region are generated by operators in smaller regions. So somehow, for example, if you have a quantum field theory generated by local quantum fields, you will expect this property to hold. And you can also think in intersection. So it's like a dual property, like this one, is that the algebra of the intersection of two regions is just intersection of algebras.
Sorry, Horacio, there is a raised hand.
Yeah, sure.
By Arif mode. Maybe you can unmute your microphone.
Okay, thank you. I have a question about the first relation and minimal requirements in ordering. Suppose if you take region R1, a diamond, and then could you have like operators on the boundary of the diamond so that when you enlarge the diamond, region R2, then because it's no longer a boundary, then those operators are not there?
Well, there are things to be. So in a quantum field theory, in general, we expect that the boundary, I mean, you mean probably the causal boundary, this corner here, and these corners are d-2 surfaces, d-2 dimensional surfaces. And so if you want to localize an operator there, you will see that it's too much singular to be a bounded operator. So all these algebras are bounded operators. And in fact, if you smear your quantum fields in a region that has d-2 dimensions, you cannot produce even an operator, even unbounded one. You only produce an operator value distribution. So really, it's expected that in quantum field theory, you cannot have operators attached to a boundary. So, and it's also related to the fact that we also think that the algebras do not have center, because if you have some operator attached to the boundary, it could commute with the rest of the algebra, producing a center. And in general, we expect that these algebras that do not have center and are what is called factors, in the sense that do not have center.
Okay, thanks.
Well, then this would be the maximal possible harmony between algebras and regions. And for example, for a free scalar, most of this is proved. Of course, in other theories, it's difficult to prove because you have to have the theory, and most of the mathematically, let's say, described, and then in general we don't have that for interacting theories. But for example, for many conformal theories, also these have improved. But then I want to study a little bit how this can be violated. I was saying that the intersection property, I will not talk much about this, because if I have this property, Hug duality and additivity, you can prove this other property, or otherwise, if you have Hug duality and additivity, you can prove the intersection property. So I will just talk about additivity and Hug duality that are more like intuitive. For example, Hug duality, you can say, well, why I cannot have duality? If I have some algebra here. I have an algebra here, and then I take the commutant of the outside, and it's bigger than the algebra here. Why I cannot just add these operators that are not in the original algebra and to enlarge the algebra here to just to have duality? The problem is that in general, if you do that, in general, it could be the case that you violate causality, for example, if you do that for all regions. So there might be obstructions in enlarging a theory to satisfy both things together. And this is what we are going to discuss now.
There is a question in the chat. Do these also apply to causal sets which are not continuous spacetimes?
Which are not continuous space-time. Sorry, space-time?
Yeah.
I don't understand well what does it mean, but if you are thinking in okay, you mean some pieces of some regions that have several disconnected components, perhaps? That applies also, yes. We will talk about that.
Mm-hmm.
If it's that what it means.
I mean causal sets which are just points, discrete points in the space-time, but not continuum. Discrete events.
Discrete events. So you mean points?
Yes.
Well,
these things that are developed by Sorkin et al. So you have causal set theory, for example.
Okay, I understand now. I understand the question. Causal sets in the sense of Sorkin. Okay.
Yeah.
No, well, this is another story that is like what he's talking about is like doing a lattice regularization of the continuous space-time with points that are somehow sprinkled randomly in Cauchy space, and then you can think also on these properties, but then it's a different story. I don't know what you can have there. Of course, in that case, in each point you can have an algebra, Hilbert space, etc. And you can think, you can try to think if you have these properties, or you can put these properties in your model, but it's a different story.
Thank you.
Okay. So one thing that we are going to assume is that so we are going to assume that the problems that so the violation of these nice properties will be related to topologies of the regions. So it can be the case that there are examples that where the violation of things are not exactly related to topology. For generalized free fields, etc., one can devise models which are worse, let's say. But let us think on that case, and let us think that there are no problems for regions that are topologically evolved. So, for example, we are assuming that the algebra of a ball is generated by the algebras of smaller balls inside the bigger one, and also that it has duality. But then let us take an arbitrary region now R with some arbitrary topology. It can be two balls, for example. It can be a ring, something like that. And then we can always define an algebra for this region that we call additive algebra, which is just the generated algebra by algebras of all balls inside R. So it's the additive net. With this, you form a particular net of algebras, which is the additive one, and it's a minimal possible one because, of course, the algebra of R has to contain the algebra of all balls inside, and then is a minimal one that you can assign to R. But then you can think, what is the maximal algebra that I can assign to this same region? And then the maximal algebra that you can assign is corresponds to the minimal one you can assign to the complementary region. Because of causality, you could take the additive algebra for the complement and take the commutant. And this is a maximal possible algebra. So the question is whether this maximal possible algebra coincides with the additive algebra or not. If it does not coincide, so our axioms are not respected, then it must be the case that this maximal algebra is generated by the additive algebra in R plus some operators that I call in here A. And the same happens for the maximal algebra for the complement. For the complement, you have also the additive algebra plus some other operators. These A and B operators are non-local. I will say more what does it mean, are non-local operators in the region R and R prime that are, we can say that are dual to each other. So in this situation, you cannot choose a net of algebras that is simultaneously have duality and additivity. Because if you take the additive algebra, so you don't take the A's, then the commutant will not be additive, will contain something more, and vice versa. So these non-local operators are not additively generated inside the topological non-trivial region R. But of course, because of our assumptions, they are additively generated inside a ball that contains R. So this word non-local has to be qualified in the sense that it's non-local in R. It's non-locally generated in R, but it's locally generated in a ball. And you can also say, prove or see that the non-local operators A and B cannot commute to each other. Because the commutant, for example, this maximal algebra, this is a maximal algebra of R, the commutant of this is exactly the additive algebra of R prime. So, so you cannot add the B operators here to R prime because they will not commute with A. Because of this relation, these A's and B's cannot commute to each other. Okay, then as these things are algebras, it must be the case that these A operators that are non-locally generated inside have a multiplication rule that produces again the same operators. It has to close an algebra. So there should be some fusion rule for the A operators and also for the B operators. In the examples I will show, these fusion rules are related to symmetry groups, to groups. So this is how the groups of symmetry appears in this scheme. And in fact, depending on the topology of the region that we choose here, where we have these non-local operators, we can have ordinary global symmetries or generalized symmetries in the sense that was described in the talks in other talks in this school. So let me begin with an example of the global symmetries. So for the case of global symmetries, the regions that have algebra region problems, they say, are regions we have non-trivial homotopy group pi 0 or pi d minus 2. Pi 0 means that if it's non-trivial, it means that the region have more than one connected component. Here I'm taking just 2 balls, for example. And pi d minus 2 is just the topology of the complement of these 2 balls. It's just something that is non-trivial because there is like a surface here that is non-contractible in the outside part of the 2 balls. So this is the type of topology where non-local operators appear when you have global symmetries. There is a thing that you have to take into account, that it's not that you have, for example, the scalar have a symmetry that phi to minus phi, but this does not have problems. But you can produce, given a theory with a global symmetry, you can produce another net that is the orbifold. It's called the orbifold. That is just taking the operators that are invariant under the global group, just invariant. So we are always taking operators that are invariant in the global group. This seems to be like a little artificial, but if you think so, if you think a little bit, you can think that these operators, in fact, are the only ones that a local laboratory can handle. For example, you cannot have in a laboratory an operator that changes the baryonic number. But still, even if you don't want to think about let's say, more philosophical ideas, you can always produce this algebra. So even the theory with the global symmetry will always give you this mathematical structure that I'm presenting here. So what are the non-local operators in this situation? Well, you can have, for example, in one ball, one charge operator, and in the other ball, an operator with the opposite charge. And the product of the two will be chargeless, so it will belong to the algebra of the theory, the global invariant and the global symmetry. But this operator does not belong to the algebra. The charge operator does not belong. So this operator that we call intertwiner, the intertwiner, is not locally generated in the algebra of two balls. There is no way to generate it by multiplying something here and something here, right? And the complementary operator is something that I draw here with this line. Is called the twist. The twist is, as I mentioned in some lectures before, the twist is just the implementation of the group transformation in a finite region of space-time. So this twist implements the group transformation only inside of this ball. And you can always produce these operators, and these are well defined, and you can prove that they exist even for theories that have discrete global symmetries. When you have a non-abelian group, then this group transformation does not belong to the neutral algebra, because it can change if you make group transformations to the twist. But you can take the sum over the twists over a conjugacy class of the group, and this is invariant. So there is always some non-local operator here. And you can see that these are not going to commute. The intertwiner and the twist they are not going to commute, because the twist will change this operator that is charged, and so they will not commute. But of course, the twist will commute with all neutral operators inside and all neutral operators inside, and the same will happen for the intertwiner. Will naturally commute with everything that is outside except the twist. So the only thing that do not commute is the twist and intertwiner. Well, the intertwiners have fusion rules that are just, the intertwiners are labeled by representation of the groups, and the twists are labeled by conjugacy classes of the group, and they have fusion rules given by the usual fusion rules of group representations and conjugacy classes of the group. And then if you think in this, if you take the additive algebra of the two balls, that doesn't have intertwiner, the commutant, of course, will have the twist, because the twist commutes with neutral operators here. And the same happens if you have the the additive algebra of the outside part, that I put this S as a kind of shell here outside. Then if you have the additive algebra, the commutant will contain the intertwiner, because the intertwiner naturally commutes with all neutral operators here. So this is a fair example where algebra and where you don't have a duality or additivity. You cannot have both at the same time. You can either choose the balls with the intertwiner, or in which case the algebra of the two balls is not additive, or if you don't take the intertwiner, then you can take the twist outside, or you can take the algebra of the two balls and without intertwiner, and the outside part without the twist, but in that case you don't have Hug duality. So there is no way to repair that. You either lose Hug duality or additivity. Now, if you have regions with non-trivial homotopy group P1, so there is non-contractible loops, or the complement of that would be non-contractible D-3 dimensional spheres. In 4 dimensions, these two things are the same. 1 and D-3 is the same. So in 4 dimensions that I will mainly talk about, they look like the same. Both of them, both non-local operators have the topology of loops. And in that case, I'm not showing here, but you can prove that the different non-local operators close abelian groups. They have to be abelian. And also you can prove that the commutation relation between non-local operators, these A's and B's, have to be of this form, where this X that I'm putting here is the character. So A and B belong to two groups, two abelian groups, and B is just the group of the representations of A. If you have an abelian group, the representation form also an abelian group, that is the dual group of A, of the original group, and then you can write this. This is a number, it's a phase, and this is a commutation relation. And the main example is the one of gauge theories. You can think, well, in a gauge theory, what could be the non-locally generated operator here? Naturally, you can think the Wilson loops that are labeled by representations. Any representation of the group can be there. But it turns out that not all Wilson loops are non-locally generated in the ring. And you can see that because, for example, suppose your theory have a charge operator under the gauge symmetry in some representation R, then you can form this operator that is is a Wilson line, is a piece of a Wilson loop, but ended on both sides, ended by an operator that is charged. So it's just a line in some segment here. And then multiplying these lines along the loop, these lines, of course, are locally generated inside here. They belong to trivial regions inside. And multiplying these things and taking, let's say, operator product expansion or the algebra generated by this, you can eliminate the boundaries, let's say, and generate a full Wilson loop. So if there is a charge operator for some representation, the corresponding Wilson loop of the same representation is not going to be non-locally generated. And if you have a non-abelian group, this always happens for the adjoint representation. The adjoint representation The adjoint, the F mu nu is in the adjoint representation, and it acts itself as a charge operator, and you can produce this type of Wilson lines to break the adjoint representation in pieces, and it's not non-locally generated. And then what are the dual operators? Well, the dual operators are with this, then you have from all Wilson loops that you can produce, only some of them will be non-locally generated. Which are the ones that cannot be generated by the adjoint representation or by other charged matters. And it turns out, for example, if you don't have charged matter, it turns out that you can classify these Wilson loops that are non-locally generated by the representation of the center of the group. And related to that, there is these other operators that are called the Toth loops, which essentially produce singular gradient transformations in this plane, let's say, bounded by B, given by elements of the center of the group. So they are given singular transformations or corresponding to elements of the center of the group. And the commutation relations are the same as I described here, where R is related to representation of the center of the group, and Z is an element of the center of the group, and this is the character. So let us come then to try to profit from these problems of algebra and regions using entropic quantities, we will call them entropic order parameters. And they will exist precisely because there are more than one possible algebra for the same region. We can take away the non-local operators, and we have only the additive algebra, or we can put them. So in order to describe how to compute these entropic order parameters, I need to introduce some quantum information theory tools. And this is called conditional expectation. A conditional expectation is a map from an algebra, let's call it M, to a subalgebra, we call N here, that is linear and positive. And it also has this property that if you have elements of the small subalgebra, they can put outside of the conditional expectation. In particular, if M is the identity, it means that the conditional expectation leaves the subalgebra in itself, leaves the subalgebra intact. It doesn't do any change in the subalgebra. So, but the important message here is that this conditional expectation is exactly what you need to lift a state from the subalgebra. If you have a state in the subalgebra and you want to produce a state in the algebra that is bigger, the conditional expectation allows you to do that. And this is the way we are using it. So you have a state in the subalgebra, and then you can produce this thing that is a state in the algebra, because you take an operator in the algebra, the conditional expectation will move it to the subalgebra, and then you apply the state in the subalgebra to produce a number expectation value. Well, in the present context, this conditional expectation I produce exactly by the non-local operators. For example, here, if I take these are the twists. If I take an average of the twist transformations of an element, it will go to the subalgebra, And this is the way all these conditional expectations are produced in this context that I'm looking at here. And then what we are interested in is in these relative entropies between, let's say, in the big algebra now, between some state that we will always take as a vacuum and some other state that is the one that was lifted from the subalgebra. So if you take discretized version, some lattice of something like that, you can see that this quantity, this relative entropy that measures the difference between the two, is just the difference of entropies. So it's a well-defined, this relative entropy is a well-defined version of the difference of entropies between a state that is a vacuum, let's say, which has all the expectation values of the non-local operators, and another state which where the non-local operators are set to 0. You see this conditional expectation will always kill the non-local operators to get to the subalgebra. So it's a well-defined way to do that. So it will measure, this thing will measure the statistics of the non-local operators. So to put all things in one diagram, one can write this complementarity diagram. You have a region, you have the additive algebra plus non-local operators, and you have the additive algebra of the complementary region plus non-local operators. From this algebra, you can go to the additive algebra by some conditional expectation. And from this big algebra, you can go to the subalgebra of additive operators by some complementary conditional expectation. And then if you take the commutant of this algebra, it will give you this one. If you take the commutant of this algebra, it will give you this one. So vertical lines are commutants, horizontal lines are conditional expectations. And you can prove that in this situation, if you have if you have a pure global state now, a pure global state, you can prove that this order parameter plus the complementary order parameter is always constant. The sum of these two is always constant. It's just the logarithm of the dimension of the group. So this we call it the entropic certainty relation by a reason that I will explain shortly. But then you can see that this thing somehow relates the statistics of, let's say, intertwiners and the statistics of twists, of the statistics of Wilson loops and the statistics of Toff loops in complementary regions. So this is region R and this is the region complementary to it. So why is this certainty relation? Well, because it's a certainty, so it's an equal here. This is the strange thing, but you can see that it contains inside the uncertainty relations from non-commutant operators. If you have the A operators and the B operators, they do not commute, and you know that there are certain uncertainty relations because they do not commute. Well, this is somehow included in this relation because you know that this relative entropy cannot be greater than logarithm of G, so this is always positive. So you can see that if you think only in this algebra, this number will be between 0 and log G. And the same here, this number will be always between 0 and log G, but they cannot have both together the maximal number because of this relation. This prohibits that both of them have a maximal number. And when you get this maximal number, when these two states are maximally different between each other, it means that the non-local operators, you remember that this kills the non-local operator, so it means that the maximal difference is when the non-local operators have expectation value 1, let's say, because they are unitary operators. So physically, what do you expect for these operators? The first thing is that when R is very thin, so suppose you have these two balls that are very small, like points. So the intertwiner will have a very little expectation value because it's just two charge operators very far separated. So it means that these two states will be very similar to each other, and then the relative entropy goes to 0, while the relative entropy in the outside part will go to log G. And then the contrary situation is when the complementary region is very thin. For example, when these balls these balls touch each other, so the twist operator has to be squeezed. This is not really a line operator. It has to be smeared, right? It has to be smeared to have a non-zero expectation value. But if the balls are very near to each other, then this smearing is very squeezed, and the expectation value of the twist will go to 0. It means that the twist expectation value order parameter will go to 0, and the other one will go to log G. And with the monotonicity of relative entropy, you can relate these order parameters, entropic order parameters, to expectation values of operators. For example, you can restrict your attention to only the algebra of some non-local operators that close an algebra, and then compute the relative entropy there, and it will be just a function of the expectation values of these operators. And you can have an upper bound coming from the expectation values of the dual operators. So you can sandwich these two things, and this is the way that you can try to compute this quantity. This is the easiest way we have found yet to compute this quantity in some particular situations. Well, what can we do with this? Well, it depends on the geometry. You can have different applications of these order parameters. Let us think in the case of a global symmetry. Again, we have this certainty relation, and it's interesting that this relative entropy of the two balls that measure the difference between having the intertwiner or not is equal. You can prove that it's equal to the difference between the mutual informations for the two balls of the full theory. It means that the theory with charge operators, now where the charge operators are considered operators of the theory, and the theory that doesn't have charge operators, the orbifold. So this order parameter is just measuring this difference of mutual informations. And as we have recalled in other lectures, these mutual informations, when you take a region and the outside part, you can think as a nice way to regularize the entropy in the limit where the distance here goes to 0. So you can study what happens with this quantity or with this relative entropy in this limit of the regularized entropy. And it happens that when these two things touch each other because of the twist gets squeezed, that you can actually compute that, and this difference is log G. So it's a finite number, even if of course, the mutual information of both theories have an area term, etc., and they diverge, but the difference is well defined and is finite. And this is what is called a topological contribution to the entropy, because this limit does not depend at all on the shape of this ball. You can vary, and you will always get log G. And the same happens. You can devise this same formula for more balls, And then you have, for example, some region A and some region B that have many boundaries, and there is a little regularization in the black curves here between them. And then you can prove that the difference of mutual information in the limit where this distance is very small is proportional to the number of boundaries. So it's really topological. Is the same formula that appears in topological entanglement entropy. Well, I didn't have I haven't mentioned what happens when G, the size of the group, is infinity. For example, for a Lie group, in that case, when these regions touch each other, you don't have a finite number. It diverges in this particular way, logarithmically with the distance. So it's like a logarithmic term in the entropy. And G, this number here is the number of generators of the Lie group. This I'm going to skip. So let me. So there is questions.
I don't see questions in the chat. Yeah.
Okay, then what happens for the case of loops? And then you can also well, here the idea was to use these relative entropys to give a notion of this topological entanglement entropy, more precisely defined, let's say. And here I'm using these entropic order parameters as order parameters. That is, for example, to prove that some generalized symmetry is, or to test what happens when some generalized symmetry is broken or unbroken. And then you can see that you can get, so you can reproduce the standard law about this, that you have a, for the dual order parameters, you have an area law for one of them, and the other one is a constant law. People can say also that this is a perimeter law, but it's better to say that it's a constant law. For example, you have in the confinement case, the relative entropy of the Wilson loops decays exponentially with the area of the loop, and the relative entropy of the top loops is approximately constant. And in the Higgs phase, the opposite case, you get the Wilson loops goes to a constant, and the top loops goes exponentially small with the area. And you also can have also the conformal case, where both of them are exponentials in something that goes like the perimeter. So L is the large side of the loop, and R is the small width of the loop. So in this situation, people say, well, you can renormalize this to be a constant because you can, but in this particular context, you cannot renormalize the operators, the loop operators, because you cannot multiply them by some other things because they have to satisfy a group law. So it cannot be done arbitrarily. So in this case, you cannot change this. It's not going to be a constant law. While in the case of confinement of Higgs phase, this that would be a perimeter law. If you enlarge the width of the loop enough, you get a constant law. You can show that, at least for the Higgs phase, that you can compute exactly this quantity. So there is like a pair of things that is a constant law for one loop, and for the dual one, you have an area law, and you have a nice heuristic picture of how this happens based on the certainty relation. The idea is that you have some loop here, and then you suppose that the complementary loop that is also thin, let's take one of these, is thin, has approximately constant law. So it means that if you change the size of the loop, the expectation value doesn't change much. And then you can use you can put many loops now, many loops crossing the other one. And with the algebra of all these loops, you can put a lower bound on the relative entropy of the outside part of this orange loop. And through the certainty relation, this will give you some bound on the other loop that will give you the area law. So so in this situation, yeah.
Sorry, there is a raised end by Arif Mod.
Yeah, sure.
Could you go back to the previous slide, please?
This one?
Yeah. So you said that this delta I is IF minus IO, right?
Yes, this is this
So,
F is the theory with charges, and this is the
right.
orbit.
Yeah. So in the gap theory, you say this delta I for these kind of regions go like this. So, and what about the gapless theory? What it's like?
Oh well, this thing for the case of two balls is always correct.
Yeah,
But when
yeah.
you have many other regions like this,
Mhm.
if the theory is gapped and there are no large distance, long distance correlations, let's say this B and this B here are uncorrelated, then you also get this. But if you have a conformal theory, you get something complicated depending. You have other terms here depending on the correlations of these things.
I see. So this would
So
be then order parameter that you could check whether the theory is gapped in the AR or something like that.
oh, this yeah, the strange thing here is that, for example, you have let's say a free fermion, and then you take the orbifold with respect to the fermion number, and then you have a logarithm of 2, and then you say, well, these entropies are different by a logarithm of 2 of these two theories, but this logarithm of 2 only appears when this size is smaller than the mass. So really, this parameter is going to be 0 unless you take this size smaller than the mass of the fermion. So it's a strange situation with respect to, and also, for example, for the fermion, a massive fermion, you suppose you have, for example, an F term, a constant term that is 0. So it's completely gapped. But the other one, the orbifold, will have then a logarithm of 2 there. So it's something strange. The topological entanglement entropy is strange in the sense that it's a gap theory, but you have a let's say a universal contribution to the entanglement entropy, a constant term there in 3 dimensions, for example.
Okay.
Yes, something is okay.
Yeah. Thank you.
Well, this was like the heuristics on how these complementary relations, area law and constant law, are related to each other. But this terminology of area law and perimeter law and constant law is somehow not the adequate in this context, in the sense that in general, when people talk about loops operators, etc., they never talk about loop operators with some width. It's always like line operators. And in this context, it's natural to think on rings, and then these rings can have any size, the width, and then it's important, this size is really important to understand. You cannot have like a zero width, because otherwise the relative order parameters are trivial. And then the natural thing to express the different phases will be rather to take some region, it can be a ring like this, and scale it smoothly, the width and the length, both together. And in this situation, somehow the terminology is simpler, in the sense that you have confinement if some of the relative order parameters go to log g, the maximum, and the other one goes to 0, and the Higgs phase in the other situation. So they are saturated, the order parameters are saturated independently of the original shape. So if I take a shape that is bigger width or whatever shape, if I scale to the infrared, I will get always this exactly the same without any dependence on the shape. And there is also the other phase, that is the conformal one, where these quantities are going to depend on the shape, with intermediate values between 0 and log g. Well, this is all what I wanted to say.
Okay, so thanks, Horacio, for a very nice set of lectures. Let's clap. Are there any questions? I don't see questions in the chat. So, okay, if there are no other questions, maybe we can thank again Horacio.
I have a question, if you don't mind. I raised my hand.
You, okay, yeah, there is a question. Arif.
Yeah, could you say something about RG invariance if somebody was, if you really want to use it to constrain the IR?
Well, of course, one thing that is would be nice to do is to understand how to control what happens in the infrared, for example, this and this or this, by the knowledge of what happens in the ultraviolet. So, for example, if you have a non-abelian gauge theory and you have a very small ring, in principle you can compute perturbatively your order parameters and try to decide what happens for the ultraviolet, for the infrared, where you have confinement, for example. Of course, this will be like, for example, to prove confinement, this will be the way to proceed. If you have some inequality that tell you that these loops are going to, under some perturbation of the ultraviolet, you are getting some of these particular things. But we do not know how to do it. For example, if you, for example, one trivial thing you can think about is monotonicity of relative entropy, but you cannot apply monotonicity for scaled regions, because this region will not be included in this one, and this one, of course, is not included in this one. There is no way, when you scale topologically non-trivial regions, one of them will not include in the other. So it is preventing to say something trivial, so it must be more complicated, and it would be nice to understand what we can say. Yeah, but there is a kind of tendency, we have seen that there is a kind of tendency so somehow the certainty relation tell you that the order parameters of the Wilson loop and the Toff loop are related to each other. And then you can think what happens with the asymmetry between them, because this is exactly maximal asymmetric and maximal asymmetric. And it looks like if you think the correlation are small, correlation between different loops are small, you can use this idea to somehow show that the asymmetry will always like increase, because if this has some expectation value that is bigger than the other. With many of these, you can still produce a smaller expectation value for this, etc. So it's kind of very imprecise heuristic ideas, but it looks like there is a tendency of increasing asymmetries between the order parameters as you move to the infrared.
Okay.
Thank you.
Okay, so if there are no other questions, let's thank again Horacio for a beautiful set of lectures. And
Thank you.
before closing for 10 minutes, let me remind you, all the participants, that you will be asked to give your feedback, your opinion about the school. Please do that, because this will help us in adjusting and improving this type of school done through web. We hope that the school will go to the usual physical format, but you never know what will happen in the future. So, okay, yeah, thanks.
Hi,
Hi,
Vitat, are you there?
Marcos.
Hi, how are you?
I cannot hear you for some reason.
Can you hear me now?
No.
Um,
Wait.
Pavel, can you hear me?
You can hear me?
I hear you, Kieran.
I cannot hear Pavel either. Let
We hear
me
you.
get out and get in again. Try it. Try. You can. Oh, I see. That's good.
We can hear you well. Can you hear us?
No, I cannot hear anyone. Okay. Let me try again. Okay. Can you again talk?
Hi, can you hear us now?
Oh, I really cannot hear you. That's very strange. What I can do is I can connect with my tablet. No, I do not hear anybody. Other apps, let me check. No. I don't. What's going on? I do not. What's going on? Do you know? Have you checked if your audio device is on? You hear sound? No, I do not. Look, people don't have to see me. I can write on the tablet and I can get in from there. Okay, let me try that thing.
He's left. Okay.
Hello, Mithat.
That you can you hear us?
You cannot hear you. You're muted.
Unmute. Okay. Now it should be okay.
You can hear us?
Yes.
Can you hear us?
Okay.
Yes, I can. Can you hear me?
Okay, excellent.
Yes.
Yes, yes.
Okay, so the students will not see me, but it's okay. I will use tablet and I will just write it, okay?
If you want, you can stay logged in with two devices.
Oh, okay. I can do that.
Okay. Remember to disconnect the audio from your iPad or tablet.
No, but he needs audio from the tablet because the audio is
Screen,
not working.
broadcast. Okay, Zoom. Something is wrong. I cannot go to my... Maybe I should... Something is wrong with my technology today. Kids were share content, screen. Okay, screen broadcast. Zoom. I cannot click on it.
Excuse me. What is the problem?
I cannot click on Zoom. You know, it says screen broadcast, and I have to click start broadcast because I panicked a little bit now. Okay.
Okay, you can see.
Okay. 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 Now I can see everything. Everything is in order. I can see my screen. So good notes. I start. Okay.
Okay, so let's start with the fourth lecture by Mithat.
Okay. So okay. This one. So today's lecture, I will discuss QCD with adjoint fermion, QCD with adjoint fermion, and on R3 times S1. Yesterday, I attended Zohar's lecture, and he pointed out that maybe two-dimensional field theories are easier than four-dimensional field theories. At least my humble opinion is that for QCD adjoint, this is not the case. At least the theory on R3 cross S1 seems to be easier to understand than the theory on R2. I worked on both of them, and you know, it gets very tricky on R2 due to reasons that Zohar explained, but on this case, it's a different story, okay? So of course we want to understand the gauge theory on R4, okay? But this is maybe very difficult, okay? Difficult. By R4, I mean R3, 1. The Euclidean construction for the R3, 1. But it turns out that it is actually possible to understand in a great detail the QCD with adjoint fermion on R2, 1 times S1. Here, S1 is a spatial circle with radius L. Importantly, it is not thermal. Okay. In my previous lecture, I pointed out the following graded partition function, Z tilde of L being trace over Hilbert space exponential minus LH minus 1 to the F. This tells us that when you make a circle, or at least on the path integral formulation, on the fermions, that we call fermion lambda, lambda of L, we impose, instead of anti-periodic, periodic boundary condition. Okay, so for fermions. Okay. Now, this construction is manifestly non-thermal. Non-thermal. That means that the thermal quantum fluctuations are not present. So there are only quantum fluctuations. And I pointed out the following. If you are on small, let's say this is R3 times S1L, which is the Euclidean continuation of this setup here. Okay, Euclidean version, Euclideanize. So, and consider this quantity. We can write down a potential for gauge holonomy, omega exponential I A4. And this potential turns out to be something very interesting. It turns out to be V of omega, turns out to be up to some prefactors, 1 over L to the 4, sum over n equal 1 to infinity, trace omega n square divided by n to the 4. Of course, this prefactor is probably the most important, one of the most important ingredient in the game. And that prefactor comes out to be nf minus 1. And the important thing is that that prefactor comes out to be, if you want to see me, okay, that prefactor comes out to be positive. Nf minus 1 is greater than 0. That means that these Polyakov loops trace omega non-tachyonic. So you can actually minimize this potential. Okay, omega is, you can view it as exponential IV1 all the way exponential IVN, and you can actually show that the minimum of this potential is a configuration of the eigenvalues where eigenvalues are maximally apart. So let's say this is one of the eigenvalue, maybe this is another one, this is another one, this is another one, and this is another one. This is n equal 5. It doesn't really matter, but this is the general pattern. So it tells you that center symmetry is unbroken. Center is unbroken. Yesterday, there was a question whether this calculation is reliable or not. And as long as we are in a regime where G square n at the scale 1 over L is much less than 1, these one loop analysis, this is one loop really, one loop analysis is reliable. Okay. There is now no doubt that QCD adjoint on very likely both on R3 times S1 as well as on R4 is an extremely special theory, extremely special and important theory. So actually, I just want to point out one more interesting property of it. Okay, since this is a lecture set for students, I want to bring a pedagogical perspective on it, one more pedagogical perspective. If you, although we will work with arbitrary NC, arbitrary SUN theory, okay, if you consider QCD with fundamental fermions, okay, and with NF species of fermions, let's say NF is much less than NC, so it doesn't really matter probably. And if you look to the Hilbert space, in the large N limit, almost the whole Hilbert space, let's say, let me just idly draw something. There are many states, of course, these are all beginning for the continuum, for the threshold. There is a bosonic state, and the first fermion in the spectrum is a baryon, and that is only for n odd. if n odd, first fermion is baryon. Gauge invariant first fermion is a baryon, and its mass is actually order n. So let me say this is bosonic Hilbert space, and this part is fermionic Hilbert space. So if you take n goes infinity limit of QCD with fundamental fermion, Hilbert space is actually bosonic. There is no fermionic part to it. Okay. So for example, this formula would not help at all in QCD adjoint. Putting a -1 to the f grading, it would not help because in your Hilbert space, there is no fermionic states. Okay. And there is, of course, in supersymmetric theory, in SUSY theory, okay, for every bosonic state, there is a fermionic state. Maybe except the ground state. There may or may not be a state here, but for every E greater than 0 state, there is a paired up fermionic state, okay? So this is bosonic, this is fermionic. And QCD adjoint, I already said, it is something special. In QCD adjoint, it is very easy to construct both fermionic and bosonic states, okay? And there is no strict alignment between bosonic and fermionic state, but the Hilbert spaces look like this. You know, if, let's say, again, these are some E greater than 0 spaces, you know, some sort of drawing some cartoon. On the other hand, the picture here, you know, is like that. This is again bosonic, fermionic, and it is actually extremely populated. Both bosonic Hilbert space as well as fermionic Hilbert space are extremely populated. Now I will make one more claim, but I will not show the details of it. If you study on S3 times S1, okay, actually you can show that center symmetry, even on R3 times S1, it is true, but on S3 times S1, you can do more calculation because of some technology developed. Actually, Kyriakos was one of the folks who developed these ideas. Center symmetry in QCD adjoint is more robust. More robust. So under some small perturbations, for example, in super Yang-Mills on R3 cross S1, you can destroy center symmetry more or less immediately, but it is very hard to destroy center symmetry in QCD adjoints. There is another thing. In this quantity, if you study partition function on, again, on S3 times S1, where S1 size is L, and interpret it in terms of L, this trace exponential minus LH minus 1 to the F, and interpret it in terms of density of states. This is strictly speaking a relative density of states, okay? Rho bosonic E minus rho fermionic E. Interestingly, the relative density of states in QCD adjoint is in agreement with supersymmetric theory rather than non-supersymmetric theories. It has a two-dimensional scaling law. It is the remnant degree of freedoms are two-dimensional. Okay.
Sorry, Mithat, can you explain the mass of the fermion is how does it compare to the scale that you're considering of the circle?
Oh, I considered. Do you mean the fermion in the Lagrangian or gauge invariant fermionic excitations?
No, the fermion in the Lagrangian.
Oh, in my Lagrangian, probably I should have written it. At this stage, I did not insert any fermionic mass. Okay, so let me G square 1/2 F mu nu square plus lambda bar I sigma bar mu d mu lambda I, and I is equal 1 to NF. At this stage, I did not put any mass for the fermion. And if you wish, I can put a mass term, lambda I, as a mass perturbation, lambda bar I. But for most of the talk, I will consider the massless theory. Is that okay?
Yeah, okay, thank you.
Okay, very good. So this is my Lagrangian. I should have written already. And okay, and I should actually also state the symmetries of my theory at this stage. Since that I have written my Lagrangian, there is already, I already mentioned that there is a one-form symmetry, one-form center symmetry that Clay introduced in his lectures. And there is also a bunch of global zero-form symmetries. So there is an SUNF rotation acting on the index I, acting on the fermions. Classically, there is a U1 axial, but this is anomalous due to ABJ anomaly. And it is broken down to, in quantum theory, it is Z to NC NF. And if you don't want to double count ZNF vectors in both, you have to divide it with ZNF, okay? That's the global symmetry. And this part is, of course, all zero form, and this part is one form, okay? Now, it should be very evident that this is probably a quantum field theory, which is not microscopically supersymmetric, but it shares many properties of supersymmetric theory. And on the other hand, as I said, it is a manifestly non-supersymmetric theory, okay? Now let's go to this theory. On R4, as I said, it is difficult, but on R3 times S1L, in the regime L and lambda less than 1, it is analytically calculable theory, okay? And I want to show this part. First of all, importantly, this construction, the fact that eigenvalues repel each other like that in this regime tells you that at sufficiently weak coupling, this theory dynamically abelianizes. So the fluctuation of these eigenvalues are fairly small. They only touch each other upon fluctuating once in a while, okay? But first, let us consider abelianization. Abelianization tells us that I can describe the dynamics, SUN dynamics. It reduces in long distances down to maximal abelian group. Note that this happens dynamically, similar to Seiberg-Witten theory, but in Seiberg-Witten theory, at least there is an adjoint Higgs in the Lagrangian. But here we didn't have adjoint Higgs in the Lagrangian. Instead, the holonomy fields upon on R3 cross S1 acted like adjoint Higgs field. Either Seiberg-Witten or Polyakov. In both cases, there is an elementary adjoint Higgs. And here in our story, this is replaced by A4. Strictly speaking, it is replaced by omega, which is the holonomy, which is compact. It is replaced by that. And whenever this condition is satisfied, if you go to sufficiently long distances, the dynamics is abelianized and described by the Cartan gluons and Cartan photons. And the reason, so in perturbation theory, therefore, there are a mu A mu1, all the Cartan subalgebra elements, a mu n, C. And for the fermions, similar structure, lambda I, lambda I1, lambda I, n, C again. Oops, okay, I changed the location of the indices, but only Cartan subalgebra entries are important. So you can write to all orders in perturbation theory, the Lagrangian just in terms of these Cartan subalgebra elements, okay? Cartan fields, okay? So, and the interesting question, and everything remains gapless. So both the photon remain gapless as well as fermion remain gapless to all orders in perturbation theory. Okay.
So sorry, Mithat, could you say one more time, please, why if we work at small n or finite n, why we can ignore the fluctuations of the eigenvalues?
Okay.
Could you say it one more time, the argument?
Yeah, very good. Very good. At small n, okay, these were the eigenvalues. Okay, I made the picture for 5. Let me be consistent. N equal 5. At small n, the important condition is n g square at scale 1 over L is much less than 1. So it is a weak coupling. So classically, so the holonomy eigenvalues are pinned down at the bottom of the potential valve, and the quantum fluctuations which would like to change them are of order g square. So this
even if you're looking at correlators at a large distance in space, not on the circle, but in the rest of the space, where the theory would normally become strongly coupled?
Excellent question. And now let me tell you what happens. Okay. So if you look to, oops, undo, and if you look to coupling constant as a function of energy, for example, if you are in theory on R4, it is of course asymptotically free. This is for the theory on R4. Let's say we consider NF equal 2 theory, which is very likely, it is asymptotically free for sure, but there is no, very likely it is confining on R4. Then there is a strong scale, lambda. But I said that at the scale, at certain scale, there is abelianization. And the scale is really 2 pi over Ln. In this theory, because of this eigenvalue distribution, the W boson mass is 2 pi over Ln. This is the important n factor, which is not due to Kaluza-Klein compactification, but because of the distribution of eigenvalues. If you wish, these masses of W bosons are the distances between these eigenvalues, similar to the W bosons in this stringy construction, okay? Now, at this scale, I said that the dynamics abelianize. It goes to become U1 to the n minus 1 at this scale. And after that, there are no charged degree of freedom in the game, which can contribute to the running of the coupling constant. Hence, the coupling constant really remains small. This is the fascinating thing about this theory. So you have g square n at the scale 1 over L much less than 1, and it remains so because of the absence of charged degrees of freedom in the game. And again, in this regard, this is similar to Seiberg-Witten theory. Okay. Now we can ask whether these degree of freedom become, gapped. For example, the dual photon becomes gapped or not. And by our experience from Polyakov model, go back to Polyakov, you may guess that monopoles should induce gap. This will turn out to be incorrect. This will turn out to be incorrect. Not the case here. Okay. Let me not say incorrect, because not the case here. Actually, there is another very important work, not as much known as Polyakov, but it is a work by Affleck, Harvey, Witten, and they discuss dimensional reduction of this theory on R3. Okay, on R3, if you consider, for example, super Young meals, dimensional reduction of super Young meals, in 3 dimension, it becomes n equal 2 theory. And you can actually prove that this theory is not confining, despite the fact that there are monopoles. No confinement and no mass gap. Now, and I will claim that QCD adjoint has mass gap for gauge fluctuation, and confinement. And it is related to both of these results. And, you know, I should make a point precise. Actually, the only distinction between this theory, from a formal looking point of view, between this theory and this theory, is that here the scalar is non-compact algebra valued, non-compact algebra valued, and here our adjoint scalar counterpart of that is compact group valued. And this will make a giant difference between these two theories. Of course, we know that the global symmetries, etc., will differ. For example, I told you that there is a discrete Z2 NFNC global symmetry, but it reduces to that because of the ABJ anomaly on R3 times S1 on locally 4 dimensions. But on R3, of course, there is no ABJ anomaly, and that symmetry is really U1A. But if you just stare at the Lagrangian, this is the whole difference between these two. And the dynamics are completely different, dramatically different. And I will explain to you both of these results. Okay. Now, let me start discussion of the QCD adjoint. Okay. Obviously, the fact that, let me discuss SU2 because it is simpler. But then I will tell you the result for SUN. Okay. SU2 gauge theory. And let us take, to be things more more interesting, let us take NF equal to, okay? So that the discrete part of the symmetry Z2 and C NF is actually Z8, okay? So same as, again, Seiberg-Witten theory, which has Z8 discrete symmetry, so that, you know, let me actually tell you what happens non-perturbatively, okay? And this is the very interesting part. And non-perturbatively, okay? Of course, because of the SU2 broken down to U1, there are monopole instantons, because monopole instantons are there because, you know, one of the eigenvalues is here, the other eigenvalue is there, and monopole instantons are just solutions. Okay, if you consider usual instanton equation, monopole instantons are solutions of the dimensional reductions of this. So let me call Fij is star dA for ij. Okay, these are monopole instanton equations that you obtain by the Bogomolny's methods. And there are such solutions, okay? And they are classified by two quantum numbers. One of them is magnetic charge, the other is topological charge. But the interesting thing is that in this theory, despite the fact that SU2 is broken down to U1, there are two types of monopole instantons. Here, since this lecture is supposed to be pedagogical, let me draw the following two diagrams. If you were, for example, a theory on R3, okay, and if you plotted, you know, phi is phi 3 minus phi 3 adjoint Higgs fields. Okay, this is a remark on R3. If your adjoint Higgs field is algebra valued, then these 2 points, are here minus V plus V. And the monopole instanton event is really the fluctuation of these eigenvalues whenever they fluctuate and touch each other and restore SU2, and there is an object there with magnetic charge. Okay, but this is the story on R3. But now look what happens when you make your Higgs fields group valued and compact. I'm making the same diagram. Okay. And I am taking this picture here and carrying down here and doing appropriate identification. Let's say this is minus V, this is plus V. Of course, these two things can fluctuate. You know, they are jittery, they fluctuate and touch each other here. This is the usual monopole, BPS monopole, or I will call it M1 monopole, okay? But they can also do the following. This can fluctuate, okay? And this has an image here, which can fluctuate, okay? And touch each other and restore SU2 again at the core. And here is your monopole, M2. It is purely there because your adjoint Higgs field is group valued, compact. And they are exactly on the same footing, okay? Now you may think that, oh, the fact that we have monopole instantons, it should tell us that there will be confinement. And it's not the case. Because look, monopole instantons are present here in the first picture, okay? In the first picture, they are present. And I claim that in that case, there is no confinement and no mass gap for gauge fluctuations. And here there will be both confinement as well as mass gap for gauge fluctuations, okay? Now, here comes write down monopole amplitude, okay? So let me ignore holonomy field. It is massive. Holonomy, it is massive. So S monopole, and it has magnetic charge +1. It has topological charge 1/2, so M1. And there is an M2 S monopole. It has magnetic charge -1, but it is not an anti-monopole, despite having magnetic charge -1, because it has topological charge +1/2. So Q magnetic for this thing is 1. Oh, Q magnetic comma Q topological is 1 comma 1/2. And for the second one, it is -1 comma 1/2. Okay. But this is not it, because there is an index theorem. Either Adia Patodi Singer, this is the old version for Dirac operator on R4 or some other manifolds, but it is crystallized by some other people, Nye and Singer. This Singer is not same as that Singer. This is Roger Penrose's student, and this is much more recent for Dirac operator on R3 cross S1 for monopole instantons. Of course, these are related. In particular, if you look to index for instanton, index for instanton on R4, this will be equal to index for monopole instanton, and these will come on A equal 1 to n in n species, okay? And you have to sum over A equal 1 to n. This is much more refined data. It tells you how many fermionic zero modes each monopole instanton has. Much more refined data. So in particular, for I was talking about NC equal 2, NF equal 2 theory. Index for the instanton is actually index for BPST instanton is 8. And index of each monopole is index monopole 1 is equal to index monopole 2, and it is 4. Okay? So you have to put fermionic zero modes. Morally speaking, they look like this. Lambda 1, lambda 1, lambda 2, lambda 2, and lambda 1, lambda 1, lambda 2, lambda 2. You have to make it SU2 invariant, but it is their structure. So if you draw it, first of all, let me make a remark. Remember, monopole instantons, in the case of Polyakov model, induced a mass gap for gauge fluctuations. But now, if you sum up all over monopole instanton events, okay, so let me, M1 is, let's say, M1 is this bunch of zero modes. This is M1. M2 is this, again, many zero modes, but there is also M1 bar, zero modes with opposite chirality. I flip the orientation of the arrow. There is also M2 bar. I flip the orientation of the arrow. So these things can proliferate in space, but the effect they generate, at least in this model, is cosine sigma and lambda 1, lambda 1, lambda 1, and lambda 2 kind of thing. So it generates a multi-fermion dual photon interaction. And now it reminds me, this sigma I defined in the last lecture, it was the dual photon in 3 dimensions. So the gauge field can be Abelianized to dual photon. This is Abelian duality. Now, there are these instanton events, monopole instanton events. And note that, let me just make a side remark concerning this, the fact that this monopole instanton index theorem has more refined data than the usual APS index theorem. You see that this has 4 zero modes, this has 4 zero modes, and if you take the product of these two, M1, M2, is morally speaking lambda to the 8, so 8 zero modes. I am dropping all the flavor index, and this is indeed the usual APS index for the Dirac operator. Okay. Now, clearly, at this level, monopole instantons cannot induce neither a mass gap nor anything else. The only thing they induce is these you know, multi-fermion interaction with the dual photon. Okay, and this is the story. So at leading order in semi-classics, which I wrote exponential Sm, and let me write this formula for in generality. Oops, I am sorry. In generality, so in general, for SUN theory, S monopole is S usual instanton, BPST instanton divided by N. It is 8 pi square G square 1 over N here, which is very important. It is important for multiple reasons, but these objects has 1 over N of the action of the usual instanton, okay? So in particular, for example, when you now consider 2 Hooftian large N limits, these configurations will survive, while usual instantons will not, okay? So usual instantons on R4 in the NC goes infinity limit, they are like of this form, so they will disappear in certain sense. The ones on R3 times S1 monopole instantons in large N limit, they will have an action NC to the 0. This is the important part, and they will survive the large N limit. But now let me tell you something interesting. So as I said, there is a magnetic charge, topological charge in the game. Okay, and there is also this was the usual instanton in 4D. There is a Z8 discrete chiral symmetry. Okay, but now this Z8 is a genuine symmetry of the theory. So that means that your effective field theory, whatever you construct, must respect to this Z8 symmetry. On the other hand, if you look to M1 monopole operator, for example, it was of this form, S monopole I sigma. Let me write it in manifestly SUNF invariant form. Determinant lambda I, lambda j, determinant is over ij. So there are, in the case NF is equal to, there are really 4 Fermi zero modes. Okay, this thing is roughly lambda 1, lambda 1, lambda 2, lambda 2, so and so. You immediately observe the following. The fermionic zero mode part of this monopole operator actually transforms under this Z8 symmetry. So Z8 action on this is negation. But I said that every effective field theory must respect the global symmetries of the microscopic theory. There is a way to undo this. How do you fix this? I have to remind you something. So first of all, so when we constructed SU2 broken down to U1, okay, and we constructed long distance theory, Fij square, and we mapped this to a dual photon, d sigma square. I am ignoring some constants. The gaplessness of this dual photon here is protected by a symmetry. By a shift symmetry, U1J. Let me call it sigma goes to sigma plus epsilon. And the Noether current associated with this is actually the magnetic field itself, because Noether current for this symmetry is, yeah. And as long as there are no monopoles, this U1J is the symmetry which protects the gaplessness of the dual photon. But we know that monopole instantons are present. So del dot J is actually non-zero because of the monopole density. okay, due to non-perturbative effects. But interestingly, a diagonal of this U1J and this Z8 symmetry, part of it acts like Z2, strictly speaking, survives. So you can actually undo this minus by changing sigma to sigma plus pi. You know, this is under this transformation. Maybe I should put a minus sign to one of them. It doesn't matter. This monopole operator, M1, M2 are invariant. So your chiral symmetry transmuted to a topological shift symmetry. It's a shift symmetry for the dual photon, okay? Now, this symmetry tells you that it is forbidden to write down cosine sigma, because cosine sigma under sigma goes to sigma plus pi goes to minus cosine sigma. And this is forbidden. But you are allowed to have cosine 2 sigma, okay? Which has, and the question is how, okay? Symmetry tells you that it is there, and you know the BPS saddles in the problem, okay? And actually now starts the relation with my discussion in quantum mechanics. This is really, again, a correlated configuration of M1 and M2 bar. Okay, it is a critical point at infinity. If you look at this picture, M1 and M2 bar, you can actually, both of them have plus magnetic charge, but opposite chirality of the fermions. So you can soak up the fermionic zero modes of one of these things, M1 plus, with the, you can soak up lambdas with lambda bars, okay? And the composite object has magnetic charge and topological charge 2, 0, okay? This is the object in the game, which is allowed by the symmetries. And despite the fact that, you know, at least in Euclidean sense, in a vague sense, these things are repulsive in the Coulomb sense, because of the fermion zero mode exchange, they can, the usual language says that they can form a pair, but the reality is exactly as I described you in my quantum mechanics lecture. These M1, M2 configuration, when they are together, it's a critical point at infinity. Only, you know, there is this interaction between them. For example, the potential between 1 and 2 bar goes like 1 over G square, 1 over R. This is a classical interaction, okay? And classical interaction tells you that this thing becomes a genuine critical point only as R goes to infinity. This is the reason that we call it critical point at infinity. But here there is a quantum term induced because of the Fermi zero mode exchange. And I think it was 4NF minus 2 log R kind of interaction. And this is quantum. That means that it is, if you put an overall factor of G square here, there is a factor of G square there, okay? Now, actually, you can, this is again a vague description, but I will give it, it can be rigorized. You can actually look at this potential, okay? So one part is classical interaction, the other is quantum interaction. You can draw it for V1, V2 bar. So V1 goes like this, it is a 1 over R decay, and log R goes like that, but log R is almost like a plateau. And the combination of these two is something like this, Okay, so there is a characteristic size which is like 1 over g square, actually L over g square, roughly speaking. Okay, but let me make these statements a little bit more precise. Okay, so there is this object, first of all. There is this object. Let me say a few words about the physics of it. Or let me make this precise, then say a few words about physics, okay? So strictly speaking, these are the, if you make a map, R is exponential tau, okay? You can actually, here, R is like separation between these defects. It is like quasi-zero mode moduli, okay? When you have these monopole instantons, they have certain number of zero modes, bosonic zero modes. 3 of them are moduli, 1 of them is angular, and there are 4 fermionic. Another one, same thing. But when they are together, the separation between them is no longer a moduli. It's a quasi-zero mode direction. And to find the amplitude for this correlated event, you have to integrate over that direction. And you can do this by mapping R to exponential tau, and you will discover something interesting, actually. You will discover that the integral over the quasi-zero mode direction takes the following form. I suspect there is a 3 here, tau. Take a form like this for M1, M2 bar. But this is exactly what we discussed in the QES and SUSY quantum mechanics. Same as. And only as tau goes to infinity, these are genuine saddles, as I draw in this picture. For example, for beta goes to infinity limit, this is the critical point. But remember my picture from the quantum mechanics class. So for the M1, M2 bar, it turns out that the most dominant, this is the critical point, both for M1, M2 bar, as well as M1, M1 bar, which also does something very interesting. And steepest descent cycle for M1, M2 bar, steepest descent cycle is this, and the most dominant configuration is that. For M1, M1 bar, steepest descent cycle, let me call it J1 or J1, M1, M1 bar. This is steepest descent cycle for this, and this is steepest descent cycle for that. And the most dominant configuration is here, somewhere there on the thimble. So these configurations are there. They are, strictly speaking, needs to be interpreted as critical points at infinity. But the most dominant configuration on the thimble is something unconventional. This is something that we call magnetic bion. This is the object with charge Q magnetic, comma, Q topological 2, 0. And this is an object that we call neutral bion, for which Q magnetic, Q topological 0, 0, but it has an effect on the holonomy potential. I will not describe that. But now let me describe physics in remaining minus 1 minute maybe. Oh, I still have 2 minutes, interesting, okay. And I started a couple minutes late. Okay, now, actually in your Lagrangian, dual Lagrangian, okay, long distance, effective field theory. Now there are multiple terms. There is this term, the sigma square. I am dropping all the prefactors, sorry about that. There are fermions along the Cartan subalgebra, sigma I, di, lambda. There are monopole terms, S monopole, I sigma, that lambda I, lambda j, minus I sigma as well there, something like that, plus complex Hermitian conjugate. But here, there is a term cosine 2 sigma, which appears at second order in semiclassics with S2 monopole, okay? This effect that appears in second order in semiclassics, it implies something interesting. First of all, it tells you that this system, okay, sigma fields, sigma field, fundamental domain of sigma field in my convention is 0 to 2 pi. And there's a potential which looks like G. I messed up my picture. Erase some things and I will fix it. This is 0 and this is my 2 pi. 2 pi, 0, pi, 2 pi. So sigma's fundamental domain. So there is this potential, minus 2s monopole cosine 2 sigma. First of all, step 0, it will cause mass gap for sigma fluctuations. Okay. And if you are in NF equal 1 theory, which is super Yang-Mills, this sigma mass gap for sigma fluctuations also translates mass gap for holonomy as well as fermion, everything. Everything is in that multiplet. Okay. And the way to see this is that these now, you can think of the vacuum as a Euclidean vacuum in terms of proliferation of these plus 2 objects. Minus 2, plus 2, minus 2. And if you insert an external charge, let's say magnetic charge, its field, instead of decaying as 1 over r, this will become r divided by c divided by r. It will acquire a finite correlation length by Debye mechanism. Okay. So, and I will not describe the confinement part. You can look to some papers or things like that. But one other interesting thing is that within the fundamental domain of this sigma field, there are 2 minima and 2 minima within fundamental domain. So one of them is sigma equals 0, the other is at sigma equal pi, okay? And this is related to the spontaneous breaking of the discrete chiral symmetry. Discrete chiral symmetry. The order parameter for discrete chiral symmetry is determinant lambda I, lambda j, and this is the order parameter. You can show that it goes as, it is, yeah. This is one of the order parameter. The other order parameter is the monopole operator itself. I sigma being non-zero, is being non-zero. Both of them are order parameter for discrete chiral symmetry. Unfortunately, I didn't have much of a time to say something on renormalons and the relation between renormalons and neutral barons. Maybe you can check the notes concerning that, or I can just take a couple minutes if Kyriakos allows me and say a few things about it, but it's okay. Either way is okay. Maybe I should stop here.
I mean, if it's going to take a few minutes, you can go ahead.
Okay. Then I want to say at most five. I want to say a few things about, so this is long distance theory. In small circle, it explains confinement. If you turn on MS for adjoint fermion, it gives correct theta angle dependence, theta over theta plus 2 pi k. some things will be function of theta over 2 pi k after inserting mass for adjoint fermion. So it explains confinement, discrete chiral symmetry breaking, and various other things. But now I want to say something about a very deep puzzle. Okay, this is originally due to 't Hooft. Actually, people thought that in QCD-like theories, okay, if you look to the Borel plane, okay, if you look to the structure of perturbation theory, there is, of course, factorial growth in the number of the Feynman diagrams. There are two sources of divergence. One of them is factorial growth in number of Feynman diagrams. And the other is coming from certain set of diagrams, a subset of diagrams, where loop integration in the presence of running coupling, alpha momentum as a function of P, induces also factorial growth. The interesting thing is the first category, 1, is related to 2 times instanton action. They are related to instanton, anti-instanton, similar to quantum mechanics. And many, many years ago, maybe 79, 't Hooft observed that if you take into account this part of the story, there are actually renormalon poles. There are actually other poles far more closer to the origin of the Borel plane. This is Borel T plane. R4, and they are located at 4s instanton divided by beta 0, 6s instanton divided by beta 0, so on and so forth. These are called IR renormalons. And there are also UV ones, minus 2s instanton divided by beta 0, that arise from studying this set of diagrams, minus 4s instanton divided by beta 0. But remember, beta 0 is, at least for Yang-Mills theory and QCD adjoint, n minus 2/3 n nf. So in particular, it is of order n. Okay. So the common consensus was that these singularities are not sourced by any semi-classical configurations. This is the common consensus. And it is a deep problem, actually. It tells you that there is something genuinely pathological about the structure of the perturbation theory in QCD. Okay, but in semi-classical domain, at least we should be able to address some part of this problem. Okay, and the picture that emerges from semi-classical domain is the following. I will just make one more diagram and stop there. Okay. At least if you calculate M1 bar, let's say in Yang-Mills, not supersymmetric cases, it turns out to have some real parts and plus minus ambiguous parts, I exponential minus 2s instanton divided by n. So there is this usual 2s instanton, and on R3 cross S1, these monopole instantons induce some singularities at 2s instanton divided by n. Okay, and IR part is same because we didn't change IR theory at all. Okay, and similarly, now clearly this 1 over n is not strictly same as beta 0. They differ a little bit. For example, if we just write down for pure Yang-Mills, the location of the singularity is 4s instanton divided by beta naught is 12 divided by 11 s instanton on R4, but 2s n, importantly n, factor of n, it is 2s instanton divided by n on R3 times S1. It is interesting. So, of course, there is this mismatch of the prefactors, okay? But it is logically possible. At least this 1 over n problem is now circumvented. You can go with these semi-classical objects by using these ideas like adiabatic continuity very close to the origin of the Borel plane here, okay? You can go to this territory at least, but these prefactors will not match, okay? And actually here, it is always 2s instanton divided by n, but here you see it is beta naught. So, and as I said, beta naught was 11/3 n minus, at least for QCD adjoint, and NF. So it also depends on NF. So this is a puzzle. It's a puzzle. I suspect that, you know, perhaps a strong interaction between monopole instantons or things like that may account for these numerical order 1 factors. Maybe can account for that factor difference. But the solution of this puzzle is not known. So actually, let me stop here. So there is indeed this very intriguing structure in perturbation theory on R4 and on R3 cross S1, and there may be some connection between renormalon and some type of M1 bar neutral bion that I mentioned. Let me stop here, and if students have questions, let me take them.
Okay, thank you, Mithat. Let's everyone thank Mithat again for the very nice lectures.
Thank you very much.
So are there any questions?
I have a question, but is for something which was quite before in the slides, if it's okay.
It's perfect.
Okay.
Yeah, no worries.
At some point, you mentioned the density of states for this partition function on the S3 times S1 with the -1 to the F, right? This.
Right.
Okay. Is there some way to explain if you take the S1 to be small? No. Okay.
Yeah. That calculation is done on S3 times S1, S3 times S1 partition function. Yes.
Yes.
Go ahead, please.
If you take and you mentioned that in the adjoint versus fundamental QCD, there is a very different behavior of the density of state at high energy, no?
Exactly.
Okay.
Yeah.
Is there some way? So there are some arguments, at least for supersymmetric theories, to compute the small L expansion, like this a paper by Zohar, Komargowski, and Di Pietro.
Yes.
You know, and then for those is related to A minus C, no?
Yes, they are.
Is there some way to extend this argument to explain if something similar happens here, so that the growth depends on the anomaly somehow?
This is actually a quite good question, honestly. Okay, very good question. Thank you very much. Fermionic of E. The thing is, you can do, at least on S3 cross S1, you can do explicit calculation. And I will tell you the result of that calculation, okay, minus LE. I think first of all, this minus sign is very important. But more than that minus sign, it is the fact that this fermionic Hilbert space is extremely populated, okay? Whenever, you know, let's say you have a trace of operators, O1, whatever it is. Whenever you put a lambda insertion there, it turns it into a fermionic operator if you start with a bosonic operator, and vice versa. You can do this kind of operator counting on S3 cross S1. And this is the work of Ofer Aharoni, Shiraz Minwala, and Papadodimas Kriakos was also on those class of works. You can look to these things and you can explicitly see what is going on in QCD adjoint. And if you look to the density of states, I actually lied to you tiny little bit, okay? It turns out that this difference, has a 4-dimensional piece and a 2-dimensional piece, okay? 4D piece, this relative density of states, and 2D piece, 2D part, okay? But this 4D piece in the large n limit has a prefactor which goes like 1 over n square. So it tells you that there is an immense calculation, immense cancellation between bosons and fermions in the spectrum in this theory. And 2D part is same as SUSY theory. And I think the deeper explanation in terms of A minus C, I think it is yet unknown, okay? But this thing is certainly there. We see it very explicitly. We see how it's happening. But it is something to be thought about, okay? So to my mind, it is very intriguing, okay? But I do not think that the deeper reason is known, okay? So let me say this. The deeper reason is not quite known. But there is clearly a very interesting structure there.
Okay, I see, thanks.
Sure.
Okay, are there any other questions? Okay, if not, then let's thank Mithat again for the nice lectures.
Thank you very much.
Thanks, Mithat.
Thank you.
And we meet again in 1 hour and a half.
Okay, sounds good. Oh.
Thanks, Mithat. It was very nice.
Thank you, Kriakos. How are you?
Fine, fine.
You are also wrapping up the school, I suspect.
Yeah, we're starting soon.
Okay. Thank you very much for organizing this. I hope it was.
No, thanks for your lectures, and it was nice.
Okay.
So can I ask you? I'm sorry. There have been some developments recently about the superconformal index and the counting of 1/16 states, which turns out that there are some subtleties in determining the saddle points when we have this fermionic. When we have this minus signs.
Mm-hmm.
Do these developments have any implications for your argument? Meaning that your argument was based on the idea that the prefactor of for the holonomy was positive, right?
Right. Yeah.
And there was a similar situation there, right? And sorry, let me remember. So the naive argument, the naive counting of the index gave a saddle point where the eigenvalues were uniformly distributed. But recently it was realized that by complexifying certain fugacities and maybe considering eigenvalues on the complex plane, you have new saddle points.
Right. And they may very well contribute, actually. It all depends on, at least in ordinary integrals, I said that there was the steepest descent cycle and steepest ascent cycle. As long as steepest ascent cycle cuts your original has a non-zero intersection number with your original integration cycle, they will contribute. So, and I think for multidimensional integrals, this sometimes becomes a bit tedious. For critical points at infinity, it becomes again understandable because you can reduce the problem to ordinary integration. But I wonder what happens, in the case you are mentioning. But if there are complex configurations, complex saddles in the game, so they may very well contribute. Even if they do not contribute as exponential of something, they will change something in the structure of perturbation theory, even when they do not contribute.
Right.
So I was a couple days ago mentioning an old paper by, not very old, maybe of order of 10 years old, by Dan Harlow and Ed Witten on level theory. There, they also face similar issues. There are some saddles in the game, complex saddles, and and if you include them, they can explain BTZ formula, but they cannot quite rationalize whether they should be included or not.
Right.
So very often in QFT, I think it's a saddle matter. We do not completely understand this question, I would say.
I see.
Yeah. But
Very good.
Very good. Yeah. Thank you again. And
yeah, thank you.
Talk to you soon at some time.
Yes, thank you.
Okay.
Bye-bye.
Bye-bye. Thanks.
We're seeing it again. The virus is spreading out of control. The president once again failing to act.
Hi, Clay.
Hello.
I think I will be your chair today.
Okay, very good.
Are you ready?
Yes, whenever.
Let us start with the fourth and last lecture by Clay.
Okay, thanks very much. So we're gonna pick up where we left off last time, and we're going to discuss the background field for the one-form symmetry. For the one form, that's a Zn symmetry of SU n Yang-Mills. And our goal here is, we're trying to discuss the background field. So just to give you a preview where we're going to discuss the background field, and then I'm going to deliver, hopefully by the end of this lecture, on the promise that I gave you at the beginning, which is that at the end of this lecture, we will be able to calculate the anomalies in SUN Yang-Mills, or at least see where they come from, and then derive an interesting conclusion. So, so this is what we were doing last time. And I remind you that we had gone in some detour through bundle topology, and what we had learned was the following. We had learned that SUN bundles are labeled by an instanton number. And that SUN mod Zn have an additional topological invariant, which we called the second Stiefel-Whitney class, and it was a cohomology class W2 in H2 of space-time with coefficients in Zn. We discussed the case for SO3, but the case for SUN mod Zn is similar. And so therefore, the SUN mod Zn path integral well, what does it look like? You have a integral dA. This is over the continuous part of the connection. You have e to the minus s Yang-Mills, which depends on a. Maybe you've got some other instances, whatever they are. Then you've got a sum over integer instanton number. And then you've also, in this case, got a sum over W2. And the range of that sum is you sum over H2 of spacetime. So that's what the SUN mod ZN path integral looks like. And it's really this piece, this outside piece here, the sum over W2, that makes it different from the SUN path integral. Okay. So after this interlude in bundle topology, I can now tell you what does it mean to turn on the background field. So recall that for SUN Yang-Mills, we have a ZN one-form symmetry, which implies that we should have some kind of background field B, which should be this kind of object. Okay. So I will now write how you do this, and you can see why it's related to what we did above. So the partition function for SUN Yang-Mills in the presence of a background B field. So the partition function should be a function of this background B field. We do a sort of intermediate thing to SUN versus SUN mod ZN. So of course, we have the integral over the continuous part of the connection. We have the sum over integer over instanton number. But then we have W2. Well, let's write it down here. W2 equals B, which is fixed in the sum, not summed over. Okay, so this is where what I wanted to show you. So I wanted to, SUN Yang-Mills has a ZN one-form symmetry, so it should be able to couple to a background B field, which is this kind of mathematical object, two-form valued in ZN. And so now I have explained what we do. So what we do is we look at the special case of SUN mod ZN bundles, where W2 is equal to a prescribed background B. That's what we're doing here. And then instead of summing over the value of W2, we hold it fixed. And we consider the partition function as a function of this B. Okay. This also, this kind of formula also tells us something useful that will play a role momentarily. So whenever you have a symmetry, you often wonder, what does it mean to gauge that symmetry? So we could ask, what does it mean to gauge the ZN one-form symmetry in SUN Yang-Mills? Well, what does gauging mean? Gauging means summing. So we will, instead of fixing B, if we gauge the one-form symmetry, we would sum over B in H2 of M with coefficients in Zn. So when the one-form symmetry is a global symmetry, we hold B fixed and we consider the partition function as a function of B. That's completely standard. And when we want to promote that one-form symmetry to be dynamical, to gauge it, we sum over B. The partition function is no longer a function of B. And what I would like you to note is that this procedure of summing over B, this reproduces exactly the SUN mod ZN path integral. So we have this this fundamental nice result. So SUN Yang-Mills plus a gauging ZN1. This is the same as what you would normally call SU mod ZN Yang-Mills. Okay, so here, let me just show you again so you see. So, up here, this is the SUN mod ZN integral, and you see the main feature is the sum over W2. Down here, this is SUN path integral coupled to a background B field. And you see that by summing over the B field, you reproduce this path integral here. So that's how we get to this conclusion. Any questions about this?
Can you hear me?
Yes, I can hear you.
Okay. If you gauge the Zn, don't you get another one-form symmetry like in 2D, like these quantum symmetries?
Yes, that's an excellent question. So to repeat the question so everyone is on the same page, the question is, if we gauge a one-form symmetry in 4 dimensions, we get a new symmetry. The answer is yes. Yes, we will get a new one-form symmetry. I don't have time to go into that in too much detail right now, but let me just say it in words, and then if you want, you can ask me again during the discussion time, and we'll unpack it a little more. But the idea is that SUN Yang-Mills has a one-form symmetry that measures the charges of Wilson lines, and SUN mod ZN Yang-Mills has a one-form symmetry that measures the charges of 't Hooft lines. And those are dual under this construction that you mentioned.
I see. Thanks.
Can I ask a question as well?
Yeah.
How do we, in the SUN Yang-Mills case, how do we actually write the background coupling? Because in Maxwell theory, you know, we have B wedge F and B wedge star F.
Yeah. So there are, I think what you're asking is how to practically enforce the condition that a bundle has W2 equals B.
Yeah.
One way, which maybe the simplest way, explicit way, is to think of, so SUN mod ZN is inside UN, right?
Yeah.
So this is familiar from, discussions of branes in string theory where we factor out the U1. So what we can do is we can utilize that, and we could write down UN gauge theory, where we factor out the U1. We think of it as non-dynamical, but we hold its flux fixed. And using that flux, we can engineer a particular B.
Mm-hmm.
Because of the fact that it's really SUN mod ZN that's inside UN and not SUN, this will give you what you want.
Okay, thanks.
Yeah. More questions?
Yes, I have a quick question. Where does the fact that ZN symmetry is a one-form symmetry come into play here? Because if I had a zero-form symmetry and I wanted to gauge that, then I would still consider SUN mod ZN bundle, even if ZN was, let's say, zero form. Is that wrong? Or?
That's wrong. So no, I mean, I'm telling you here. So it comes in various places. So first, the fact that it's a one-form symmetry tells us the kind of object that we want has this upper 2 here, right? It's like a 2-form background field. This is a background gauge field, right? So if you have a 0-form symmetry, the background gauge field is like a 1-form locally.
Yes.
If you have a 2-form, you have a 1-form symmetry, the background field is locally a 2-form. So that's one place. The second place is that I am giving you an extremely specific, though it may not feel that way because it's a bit abstract. I'm giving you a very specific way in which the B field the one form symmetry couples to the theory and how to turn it on. I'm telling you what to do. You're supposed to sum over a restricted class of bundles. So that's very particular to the dynamics of this Yang-Mills theory.
Okay, thanks.
More questions?
There's okay. There was some question in the chat, but I think it was addressed by Cantaro. Well, it was about some sort of unconventional use of W2, related to your unconventional use of W2.
Okay. Well,
I think it was addressed by Cantaro.
Okay. If it was addressed and it's about conventions, then I will definitely skip it. Okay. Okay. So maybe let's keep going. So what have we done? We've introduced the concept of one form symmetry. We've introduced the concept of background fields. And we know how at least in principle, we know what to do for Yang-Mills. And now what I would finally like to discuss with you is the anomalies of Yang-Mills theory. So this is what I advertised at the beginning. Okay. So so remember, so we're going to discuss anomalies in Yang-Mills. So remember very generally that, you know, what we said at the beginning, if you have a partition function that's a function of some background field and you try to do a gauge transformation, you can often detect an anomaly by the failure of background gauge invariance. And the failure is by some local functional omega. So this is how we utilize partition functions to find anomalies. And we're basically going to do something extremely similar here. So we're going to consider an example with one form symmetry. And of course, our example will be SUN Yang-Mills. And now we'll have to remember the theta term. So I remind you that the theta term is the following: theta over 8 pi squared. Always important to get that factor right, especially in what we're going to do now. Integral over space-time, let's call space-time M, of trace f wedge f. And that trace is in the fundamental. Okay. So we have our background. We have the background B. Continue to call it B for Zn1. And correspondingly, we have some partition function Z of B. Okay, let's begin with a simple question. So the question is, can there be an anomaly involving only Zn1? So without other symmetries, without consideration. Okay, so let's see if this works over Zoom. Let's see if one of the students can chime in and try and answer that question. Pauses are much less awkward for me over Zoom, so I can wait a little while.
we consider the definition of ZB to be in the second homology class. So it's invariant up to gauge transformation, right?
Well, but why is it invariant? I mean, how do you know I didn't make a mistake? All right, anomalies are always about making a mistake like that. So how do you know that I didn't make a mistake?
Isn't it by the definition of ZB to be?
No, I mean the way to argue would preclude the existence of any anomaly ever, because you're saying, well, isn't it by definition that the partition function only depends on the gauge equivalence class of the background? So there is something to think about here, right? How do you know? There should be a way now that we know in our bones that there is the answer to this question. Any other takers? Okay.
Probably the best answer, but I think you said that you can gauge the symmetry to get SUN mod ZN.
That's an excellent, yeah, indeed. So that's the answer I was looking for. Answer, no. As we just discussed, gauging ZN1 leads to SN mod ZN. A good answer. SUN mod ZN Yang-Mills, we know this theory exists. You can forget everything that I told you about in these lectures. If someone came up to you and asked, does SUN mod ZN Yang-Mills make sense? Your answer should have been yes. So whatever formalism I have introduced and played around with in the last few days, it certainly can't change that. Okay, so what do we conclude from this? Conclude that any for ZN1 must, if it exists at all, involve another symmetry. So there can't be anything like a pure ZN1 anomaly in Yang-Mills theory by this argument. But there could be anomalies involving other symmetries. And in fact, I have mentioned another symmetry earlier on, and that will play a key role here. That symmetry is time reversal. Which I called T. Okay, so what we're going to do now is we're going to sketch the derivation of an anomaly that is an interesting mixed anomaly between time reversal and the one-form symmetry. Okay. So in order to do that, we're going to have to undergo a little interlude on the periodicity of theta. So theta here means the theta angle in Yang-Mills. So let's start. For all SUN bundles, what do we know? We know that I, which is 1/8 pi squared, integral over space-time of trace F wedge. That trace is then the fundamental, that this is in the integers. And so the theta term, is exponential of I theta big I. And so theta is 2 pi periodic. Okay, so far so good. But now you should look at what I said here as the caveat. For all SUN bundles, as we were discussing above, when we turn on a background B field, we're exiting the universe of SUN bundles. So we have to reinvestigate this periodicity of theta in that situation. Is that logic clear to everyone?
And sorry, can you repeat it once again?
Okay, so okay, so let me just scroll down. If B is on, non-zero, this is the background for the one-form symmetry. That means we are studying SUN mod ZN bundles with W2 equals B. Right? If we go back up here, discussing this, right? This here, right? This is what it means to turn on the background field, B. It means we turn on W2 equals B. We don't sum over W2, but we hold it non-zero and on. So in this case, when we're discussing the periodicity of theta, we need to be careful, because while we know that I is an integer for all SUN bundles, once the background field is turned on, you're outside the universe of pure SUN bundles. Does that make sense?
Clay, there are some questions about this follow-up on absence of anomalies. So there are two questions. Well, they're more or less the same, so I will take one of them. There's a question from Ahad. Wouldn't both the definition of SUN mod ZN and the fact that we can gauge the one-form symmetry to get it require showing that the partition function Z of B of SUN does not depend on the representative B of a class of B in second cohomology we choose in advance?
Yeah, that is basically the argument that I gave. So if I'm understanding correctly, the argument that I gave was that the existence of SUN mod ZN, Yang-Mills, the fact that that quantum field theory is consistent, and the fact that we can interpret that quantum field theory as SUN Yang-Mills together with gauging the one-form symmetry, that fact tells us that there are no pure one-form symmetry anomalies in SUN Yang-Mills. That is exactly what I was trying to say. Okay, so we're back down here. So we have to ask this question: what about the periodicity in SUN mod ZN? And here we will discover something interesting. There are fractional instantons. And this will be the key gauge theory feature that leads to something nice. So let me write it down. I'll write down a formula. Okay, I'll write it down and then explain a little bit of technical baggage that I'm carrying around. So we use the same formula for I. So I claim that this is no longer in general an integer, but rather takes the following form. Okay, so let me unpack this a little bit. So first of all, some little fine print for the cognoscenti in the audience. I'll assume that M is a spin manifold. And simplicity, I'll assume that N is even. And also this notation W2 cup W2, you can, if you like, think of it as essentially W2 wedge W2 if you were doing forms. Okay, so what's the point of this formula supposed to be? So first of all, we know that if W2 is 0, we're really talking about an SUN bundle. Right, we learned that last time. And then you see that then in that case, this first funny term goes away and you end up with just an integer. So that's at least a little simple check about what we expected. But more generally, you see that in SUN mod Zn, the instanton number is not in general an integer. Instead, it has a full part. The fractional part is controlled by this integral. Fractional part of I is controlled by W2. Okay, so that that may seem a little funky. So let's do an explicit example. Okay, so how will our explicit example make an abelian A inside SU2 mod Z2? That's the simplest case where this stuff is supposed to work, which is the same as SO3. So that was where I told you about what W2 was anyway. So that will make it easy to work in this situation. Okay. So let's give some details. First of all, before going into the details, are there questions about this equation, this claim about I? Does it? Do you understand mathematically what is being claimed? Okay. No?
Yes, but can I ask what changes when n is odd?
Not much. Some denominators and things like that. Not much. I mean, yeah, not much.
Okay, thank you.
Something later would change if n was odd. So you can ask me that question later and I'll try to answer it in better detail.
All right, thank you.
And can we check if we were to sum over W2, then this term does not contribute?
If we were to sum over what, sorry?
If we were to sum over bundles.
If we were to sum over bundles, this
Yes.
term.
Right.
Why do you believe that that should be so? You mean if you sum over W2?
Right.
Yeah, there's no reason that should be so. That term is important. If you're doing, part of the lesson here will be that you need to be careful about the theta term in SO3 gauge theory, for instance. So there's no reason, and in fact, well, it does not true that W2 squared term drops out.
No, if I were to sum over all the bundles, then I should get SU2 bundle, right?
No. Summing over W2 is the same as summing over is the same as being in the SO3 bundles.
Okay, yeah, I had the story upside down. Okay, thanks.
Yeah, remember, it's a little bit funny. SU2 is the bigger group, but SO3 has more bundles.
Gotcha.
More questions? Okay. Okay, very good. So we're going to do an explicit example. So we will take space-time to be T4, so a 4 torus. And we'll identify the coordinates as follows. Xi is identified with xi plus 1. Now, I promised you an abelian gauge field so that it's pretty simple. So we'll take A equals AI. It has only a 3 component. 3. This is the Lie algebra label. And it will be multiplied by sigma 3 over 2. Sigma 3 is the standard Pauli matrix, diagonal 1 minus 1. And then, of course, to make it a form, we put a dxi here. Okay. So what will be our connection? Okay. A1 will be pi x2. A2 will be minus pi x1. A3 will be pi x4. And A4 will be minus pi x3. Okay, so this is a little bit of a tricky connection. How do you check that I've got all my factors and so forth correctly? Well, one way to do it is to work out what the flux is. So that's easy enough to do. So F12, this is equal to 2 pi. And F34 is equal to 2 pi. And all other f's are 0. So in other words, so my flux is properly quantized. In other words, f over 2 pi as a differential form is dx1 dx2. There's a wedge there, plus dx3 wedge dx4. Okay, so now we can compute. So first of all, let's evaluate W2. So remember, I told you that if you have a SO3 connection, which happens to, as a special case, be an abelian gauge field, then to get the value of W2, you just take the magnetic flux, that is F, and evaluate it mod 2. So we can integrate W2 over the 1, 2 torus, the torus with x1 and x2 directions. And this is, of course, just looking here, this is 1. And we can integrate W2 over the 3, 4 torus. And this is also 1. So what we conclude about this is that so this bundle doesn't lift to SU2. This is really a bundle with non-trivial discrete magnetic flux, non-trivial W2. And so we can find something interesting here. Okay, so let's go up to here. We have this term here that we were supposed to evaluate, this fractional thing. So let's do it. Oops. So 1/4 integral W2 cup W2. So we're supposed to square F. So we only care, now we're integrating over the full T4. So this is 1/4 integral over T4 dx1 wedge dx2 plus dx3 wedge dx4 squared. So we get a 2 from the cross term. The only term that contributes is the cross term. So we get a half. Okay, so we got something interesting there. Now we have to compute the instanton number. Meanwhile, let's see if now the moment of truth, we'll see if I get all my factors of 2's and pi's really correct. I is 1 over 8 pi squared, integral over T4. Again, we have f wedge f. Okay, let's see. dx1 wedge dx2 plus dx3 wedge dx4 squared. We have 2 pi squared because this is here, because this is f over 2 pi. Oops. And let's see, and then we also have of sigma 3 over 2 squared. Okay, so let's see what we get. So let's see. So the cross term here again gives me a 2, and then I've got here. So this is 2 times 4 pi squared. Sigma 3 squared is the identity. Trace of that is 2, and then I've got 2 2's in the denominator, so I've got a half. So in combination, the whole thing I is again equal to 1/2. Okay, so so what happened? We produced an explicit instanton with number 1/2. And we saw that that 1/2 is the same 1/2 as we expected from that is controlled by W2 squared. That's from our general formula up here, that the instanton number is in general a fraction, but the fractional part is completely fixed by W2 squared. Okay, any questions?
There was a question in the chat about anomalies, but I think it was also answered by Kantaro.
Okay, I'm glad to have Kantaro on my team. Okay, so
there's a new question from Isa.
Yeah.
Can one find an explicit, non-trivial, space-time dependent fractional solution in the PSUN?
Say it one more time, Pavel.
Can one find an explicit, non-trivial, space-time dependent fractional solution in the PSUN case?
Sure. I mean, I just did that. I'm not sure what space-time dependent means, but I mean, for SO3, which is PSU2, here is an A. The A depends on position. The flux is constant, but the A certainly depends on position. Indeed, one can do this explicitly for SUN on ZN as well. And I think there is a literature about explicitly exhibiting fractional instantons on various manifolds.
I don't know, maybe the question was non-constant, also non-constant F. I don't know.
Yeah, I'm sure that that can be done as well. But I think on the torus, the example that I gave you, I mean, I called it an instanton, but I didn't. You might have also asked, could I find a self-dual solution?
Self-dual.
Yeah, and mine is self-dual.
Yeah, but what I meant is that it needs to be dependent on space and time for the field strength, like the usual instanton solution.
In order to be self-dual, you mean? In the torus, I think the example that isn't the example I gave self-dual?
No, it is self-dual, but it is a constant solution. Both you wrote electric field is equal to magnetic field, and it is just throughout the space, both of them are constant.
I suspect if you look on CP2, you'll find something pretty interesting. That's probably the first case where you, that's probably a place to look to find explicit solutions. I'm not sure what the status of the literature is there, but I suspect that you can find explicit self-dual solutions, which would have to be position dependent. But let's talk about it later.
Okay.
Okay. So okay, so we see fractional instantons. So fractional instantons, what was the point of this? Well, imply that there is a larger theta periodicity. So in particular, one concludes that in SUN mod Zn, theta is not 2 pi periodic, but theta is 2 pi n periodic. So here again, I remind you that we always define theta to be the coefficient of 1 over 8 pi squared integral trace f wedge f. And so when we do that, because of this fact that this integral can now be fractional, the periodicity of theta is larger. It's fractional, but its fractional part is controlled. We know how bad it can get. And so that's why we get this n. We just examine the general formula that I wrote, and we see that the minimum fraction is 1 over n. The maximum fraction is 1 over n. Okay, so now we're ready to put it all together. So
there's a question in the chat.
Yeah.
So the question, well, as far as I understand, is following. So if we add matter fermions, there can be continuous symmetry, and the question could there be in this case a mixed anomaly between Zn and continuous symmetry?
The question is, can the anomalies involving involving the one-form symmetry and matter fields? The answer is in general yes. Okay, so the final topic, explicitly say the mixed anomaly at theta equals pi. And here, again, I will restrict for a technical reason for n to be even. And people who are interested in the fine print can ask me about that later. Okay, so let's say all the things. So we know that the B field for SUN1, for ZN1 is W2 of an SUN mod Zn bundle. That was just the definition of what the background field was. So what we're supposed to ask now is if B is not equal to 0, is the theory T invariant? This is our question. So remember that time reversal acts on theta by sending it to minus theta. All right, we discussed that before. Why was that? We discussed it in the first lecture. Well, f wedge f has the epsilon symbol in it. So acting with t changes the sign here of epsilon. And so we can think of that as changing the sign of theta. So in other words, to check whether the theory was time independent and time invariant at theta equals pi, it was already a little bit tricky. We had to use the fact that pi and minus pi are congruent modulo 2 pi. Right, so in other words, we have exp of I, usually we have I theta instanton number. In the case where theta equals pi, this is the term in the action, e to the I pi instanton number. Now let's act with t. This is e to the minus I pi instanton, which we can write as exp I pi I times exp of minus 2 pi I. So this is the original thing. That's the original term in the action right here. And this is what we potentially might be off by. So this here equals 1 if b equals 0, right? That was the usual periodicity, but not anymore. Instead, when b is non-zero, we have exp of 2 pi I equals exp of 2 pi I over 2n integral over space w2 w2. So here in this step, I am using this formula at the top of this page right here, that the instanton number is an integer plus a fraction controlled by w2 squared. So 2 pi I, e to the 2 pi I integer, that's 1. We don't care about that. All we care about now is the fractional part. So coming back down here, we have formula e to the 2 pi I instanton number is e to the 2 pi I over 2n w2 cup w2, and w2 is b, right? B is ground field, and that's equal to w2. So this is finally exp of I pi over n integral over spacetime b cup b. And this is not 1. So what did we conclude? We concluded that with background B on, T is in general broken. This is what you usually mean by a mixed anomaly. Right? An anomaly in quantum field theory, you mean that you turn on a background for one for one symmetry, and you find that a companion symmetry is broken. Here we see that explicitly. In this situation, we turned on a background field for the one form symmetry, the Zn one form symmetry. That was the background field B. And then we did a little calculation, and we found that time reversal is just broken. So this is our conclusion. There's a mixed anomaly between Zn1 T. So this, and this is at theta equals pi. Okay, so just to sum up, we can now deliver and connect back to the initial discussion about anomalies in quantum field theory in lecture 1. So there we discussed that any theory with anomaly, so since a theory with an anomaly cannot be trivially gapped in the IR, we conclude that SUN Yang-Mills at theta equals pi cannot be trivially gapped. So something interesting has to happen at long distances in SUN Yang-Mills at theta equals pi. And exploring what that something is, well, that's a subject of a whole nother series of lectures. So I think I'll stop here and take questions.
Let's thank Clay for his nice series of lectures.
I have a question. Can I?
Yes, please.
So usually when you define anomaly, you also have to discuss the local counter terms, no?
Yes. Yeah. Excellent question. So the question is, how do I know that this cannot be eliminated by a counter term? That's an excellent question, and I kind of skipped it for time reasons, but it's really a key question. So let me write it. Can this be eliminated by a counter term? So the kind of counter term you would want to write is exponential of, I guess it's 2 pi I over n. Well, let me not worry about the question for a minute. You want to write something like b cup b with some number here. And you want to know if you can choose that number to eliminate this feature. And what you will find is that for n even, you cannot choose the number. To eliminate the anomaly, to eliminate the transformation. For n odd, you can. So the correct conclusion is that for n even, there is this anomaly, and for n odd, there is not, because of the existence of this counter term. And a more sophisticated argument is needed to say something about n odd.
Okay, great. Thanks.
Sorry, a very naive question. Like, why can't I just choose this number to be minus pi over n, and that would cancel the anomaly? Sorry, I'm probably being very naive, but.
Well, what you want to check is that if you do time reversal, that you absorb this transformation, right? Over here, we found that if we do t, something is spit out.
Yeah, you got exponential.
You'll have to investigate how is this number transforming under t. This is like b wedge b, so it's also got some epsilon in it. So that number itself is not inert.
I see. Okay.
So would you say that there is no mixed anomaly for n odd?
Yes, that's correct.
There is a question in the chat from Hossein. Out of curiosity, is there any connection between topological susceptibility and Q-form symmetries?
Probably the answer is yes, but I'm not completely qualified to answer it.
So for B turn on, so theta is equal to pi is no longer time invariant, but some other theta would be, you know?
Some other theta. No, when B is on, theta has gotten this much larger periodicity. So
yeah, so it has larger periodicity. So some value of theta would be t invariant. That's what my question is. Like when theta was 2 pi, when the range was 2 pi, then theta is equal to pi, the theory was t invariant.
So I think what you are asking about is what is the t invariant theta angle in SUN mod Zn, and indeed there is a middle value there that is
exactly
t invariant. Yeah.
Okay, but that would not be relevant for. I mean, this argument still stands.
This argument still stands, but that would be important for investigating the time reversal properties of say SO3 gauge theory.
Right. Okay.
Clay, can I ask a question?
Yes, please.
What happens is more about then the analogues of this type of argument. You know, theta equals pi in SUN coupled to matter. What's known about doing this type of argument for SUN Yang-Mills with matter? So, for example, you know, for instance, super Yang-Mills or QCD.
Yeah. So, in fact, I wrote a paper about that. It's a little bit tricky. Some stuff starts to depend on like number theoretic congruences of the, or common divisors of the number of quarks and the number of gluons, and the rank of the gauge group. So one of the papers that I put in the reference is a paper. It's called like Anomalies in the Space of Couplings 2 by myself, Nadi, Hotat Lam, and Dan Fried, and it's got a lot of examples like this. So there are. We didn't study it exhaustively, but we did study it for, say, SUN coupled to fundamental matter. And there, what happens is that the one-form symmetry is broken. So because you can screen the Wilson line. So you might say, well, maybe there's nothing else to say. But that's not true, because the flavor symmetry can sort of can sometimes take up the part of the one-form symmetry. So you can have an interesting anomaly there. And whether or not you do depends a little bit in detail on the number of flavors and colors, but we've worked out some examples, but by no means exhaustive.
And what about with adjoint matter, like in super Yang-Mills, where you still have the one-form symmetry?
Yeah, so for adjoint matter, indeed, many of these things just go straight through. Many of them just go straight through. So I think this anomaly, I think, is just still. I think it's just still present.
I have a question.
Yeah.
I was wondering what will happen if we have a phase transition in between, and we want to
where and as a function of what?
For example, we have this anomaly in UV, and this mixed Zn one form and T anomaly. And then, I don't know, like, for example, we have a symmetry breaking and like a global symmetry breaking, not like Zn symmetry being broken. And then we want to match this anomaly in the low energy in IR. Then will the theory develop in an quote unquote strange case, or like most of the cases, it's the anomaly matching is straightforward?
Sorry, someone is calling me. So okay, I mean, the most detailed thing that I can say about that. So I mean, it depends the way the anomaly matching works. If you try and reproduce this anomaly in various different phases of hypothetical phases of the Yang-Mills theory, the way that works depends on what infrared fields are available to you. But there is this result, I called it result 2. That I mentioned before, so which says any theory with this Zn1 T anomaly cannot be simultaneously, let's see what it was. It was gapped, confining, and T invariant. So, you know, that's the strongest constraint that I know on realizing this anomaly in various different phases.
I have another question.
Please.
Is there another way to see this mixed anomaly by adding some background gauge field for both T and the Zn one-form symmetry at the same time and showing that the partition function is not gauge invariant anymore?
For both T, did you say T and the one
Yeah,
form?
right.
Yes.
Yeah.
Yes, absolutely. In fact, that might be in some ways a more principled way of doing it. What I did is kind of the fastest way. The reason it's a little bit tricky to proceed the way you suggested, even though it's by far kind of conceptually the best way, is that what is a background field for time reversal symmetry? So time reversal is a space-time symmetry. So a background field for time reversal symmetry means that the space-time manifold becomes non-orientable.
Right. Yeah. So you could study
So
it on.
you would you would have to get into discussing all these little topological facts about bundles and cup products and all these things on non-orientable manifolds, and danger lies ahead. Let me put it that way.
Okay. Thanks. Yeah. Is it done somewhere? Do you like?
I think it is done in a paper by Dan Fried. Yeah.
Dan Fried. Okay. Thanks. Yeah.
In the presence of supersymmetry, I expect that we'll have to supersymmetrize this term of B cup B. Is that correct?
I don't think so.
No? Okay. Why is that?
Well, it's already topological.
I see. So you expect B to be sort of in the kernel of all the supercharges?
It's a discrete field, so I think so. Yeah.
Would that be true for the case of U1 one-form symmetry as well?
No. Then there's something local. So in that case, I think the B field. There's no corresponding current. So where I'm certain that you'll have to supersymmetrize something is if there's a local operator that's related to this discussion, and then certainly that local operator will come in a multiplet. So for instance, if you have U1 one-form symmetry, then you have a conserved higher form current, and that current certainly would have to come in a multiplet.
Right. Great. Thank you.
Okay, maybe we postpone first questions to tutorial because we would like to make a short break before the tutorial, which will start in 5 minutes. But let's thank again. Okay, 5 minutes, in roughly 5 minutes, we will have a tutorial on entanglement. And yeah, I would like to remind you that we want to give you a kind of feedback about the school in the form of a quick survey. I put a link in a Zoom chat, and you also get it by email. So it's quite important for us because we are kind of inexperienced in this type of virtual schools. So the feedback would be very welcome. And it takes like about 2 minutes to go through this survey. So you can do it right now, or you can wait till the very end of the school.
Pavel, am I also supposed to do this survey?
Yes, please.
Oh, by the way, Pavel, it didn't happen fast enough, but for me to respond to you, but there is an alternative to Slack that is very, very good for math and physics discussions because it has completely integrated LaTeX.
Is it right?
It's called Zulip. It's very similar. The interface is extremely similar, but it you can just type LaTeX and it will compile it in the chat without any added plugins or whatever other hacks you have to do for Slack.
Okay.
So that's what I do that's what I have going in my group.
How is it? Zulip?
ZULIP.
Okay.
It's owned by Dropbox. And it's a similar pricing model to Slack, where you it's free up to some 10,000 messages or something like that, and then after that you have to start paying.
Yeah, because with Slack, you like on a free account, you can do almost everything.
Yeah, it's the same with that. It's just that there's a message cap, right? Like with free account with Slack, if you ever hit 10,000 messages, it'll start deleting the earlier ones.
Yeah, so far we decided just to go with the kind of most popular choices.
Yeah. But if it goes into the future, or I'm just saying it in case you care to know, I do find these chat apps to be very useful, but it's nice if they have